Get your notes out. Let's see what we can do this. Final exam review. Final review. Now, after this, we will continue to learn some more things about AP Calculus. And again, your grade can continue to improve after this. But this will be a pretty big part of it. So the three main branches, three branches of calculus, branches. We have limits, derivatives, and integrals. Oh, goodness gracious. Sorry, everyone. Sorry. Share the right board, Mr. Mitchell. Integrals. So we're going to go through these like piece by piece. Let's start with limits. What do you need to know about limits? What do we need to know about limits? The definition of a limit. First, the definition of a limit. You will always be tested on whether you know what it really means. The definition of a limit, as x approaches some value of f of x, means that the limit from the left is equal to the limit from the right, right? To have a limit, you need to have both sides approaching the same place. Limit from the left has to be the same as the limit from the right. That's how you know you have a limit. And the purpose of limits was to enable us to do things like define continuity and differentiability. Continuity. So the definition of continuity, to have a function be continuous means there's three parts, right? One, the limit of x approaches c exists. 2, f of c exists. And 3, the limit as x approaches c of f of x equals f of c. This is our definition of a limit, of continuity. The limit exists, right? You have to have a limit available, right? The limit exists, so we have two things approach the same location. The limit exists. That means you have a left and a right. To exist, you have to have a left and a right, right? So we have this like double definition. F of c has to exist. We have to have a point, right? A location. And the limit and the point have to match. So these two pieces added together give us this definition of continuity, right? So this is really the key definition here. Continuity. For something to be continuous, the limit has to equal the point at a certain location, right? That means the left side and the right side have to be the same. So you can test those kinds of things. That's what we mean by continuous. So I'm going to go real fast because there's a lot to cover. Limits also allow us to do something with the definition of, well, it also defines the derivative. The definition of the derivative. Definition of the derivative. Do little points here, dots. We have a limit definition of the derivative, and the definition of the derivative is the limit as x approaches some value of f of x minus f of that value over x minus that value. It's basically a slope, right? This is like rise over run. And this is equal to the derivative at that point c. This is the limit definition of derivative. As x approaches some value, right, it's f of x minus f of c over x minus c. We did a lot of these way back when. I made you do a lot of these by hand, right, where I had you simplify and then you had to cancel something and you got a derivative. we have other rules for derivatives now, but this was the limit definition. And oftentimes they throw this definition in there. They give you an equation. They're like, oh, here's a weird equation. And what they really mean is take a look at the function here and just do the derivative. They give you this equation. They say, oh, it's the limit as x approaches 2 of f of x minus f of 2 over x minus 2. They really mean find the derivative. They really mean find the derivative. So that's what the limit definition of a derivative is. You'll see that sometimes and have to know how to translate that. So understand that this means just you're finding a derivative. Other things that limits let us do is the intermediate value theorem. Intermediate value theorem. This means find the derivative. So the intermediate value theorem is another thing that limits allow us to find, right? The intermediate value theorem says if f of x is continuous on some interval a to b, right? Then it takes on every value between f of a and f of b. So this is the definition of the intermediate value theorem. So basically, the intermediate value theorem requires continuity, right? Key things about this: requires continuity, meaning there's no holes, no asymptotes, and no jumps. It requires continuity of the function. Most functions are continuous, right? If there's a asymptote or a break, or if it's a piecewise function, they love to give you piecewise functions. If it's a piecewise function, check to see if it's continuous before you can do it. So the intermediate value theorem basically says if you have a graph, right? If you have a graph that starts at A and ends at B, and you have some value here, f of A, and you have some value here, f of B, we know the graph is everywhere between, it's going to touch all the values between f of A and f of B. So if I start at, let's say I start at 2 and go to 10, right? Let's say I start down at 2 and go to 10, right? So that means that every value, somewhere in this range, my value is going to be, I don't know, 7. Right? It guarantees every value between 2 to 10 in this range, because that's what the intermediate value theorem says. As long as my function is continuous, then it takes on every value between 2 to 10. Can I be sure is f of x equal to 11 somewhere? We cannot say for sure. Cannot say for sure. But if I said like is f of x equal to 5? Yes, because of the intermediate value theorem. Right, so you're checking to see what the bottom value, what the top value is. And how do we know there's something between 2 to 10? Well, because our function is continuous, because f of x is continuous on a to b. So because we know the value, because we know the function's continuous, we know that there's this value 5 because 5 is between 2 to 10. We can't say for sure about 11. It may go up to 11, but we cannot say for sure because 11 is outside the boundaries, right? So that's the intermediate value theorem. And the reason we're allowed to do this is because we have a definition of continuity now. Right. So that's the summary of limits. What limits let us do, right? This derivative definition, intermediate value theorem, all those things. Also an extreme value theorem. So that is limits, right? Let's talk about the next branch, derivatives. Derivatives. What do derivatives allow us to do? First of all, when I say derivative, you say slope, right? A derivative is the slope of the tangent line. So what are some things you need to be aware of? First of all, you need to be aware of the derivative rules. Right? The derivative d dx of x to the n is nx to the n minus 1, etc. All the rules, right? The quotient rule, product rule, chain rule. The quotient rule, product. I guess I'll just list the rules here. Oh goodness gracious! Stop it! Stop it! Stop it! Stop it! Stop it! Quotient rule. Quotient rule. Quotient rule. Chain rule. The product rule. What else? Quotient rule, chain rule, product rule. Those are the main ones. Power rule here. This is the power rule. Right? Know how to do the derivative of a square root. d dx of square roots, right? You should be able to know the derivative of ln is 1 over x. You should know the derivative of the trig derivatives. You should know, what else? The derivative of e to the x, d dx of e to the x is e to the x. Trig derivatives. I think that's mostly it. All those derivative rules we talked about. We also have, you should also be aware of the graphs of derivatives, right? The graphs, what the graphs look like. Graphs of f and f prime. You should be able to identify between, if I give you the graph of f, you should be able to picture what the graph of f prime looks like, right? So if this is f prime is going to look like what? Well, we have negative slopes, then positive slopes, and then a 0 slope. So it's going to be negative, then 0, then positive. Right? You have positive slopes over here, positive slopes over here, so this is going to be a positive section. Negative slopes down there, and then it goes 0 right here. So 0 is when you cross the 0 axis, right? This is a 0 slope, crosses the 0 axis. And if I give you a graph of a derivative, if this is f prime, let's say I have a derivative that looks like that, what does the original graph look like? If I give you a derivative, what's the original graph look like? So you should be able to tell at this location, at this location, and at this location, these are maxes or mins, max or min, right? When it goes from negative to positive, right? We have negative here, and then it goes positive, right? This is a minimum here. Positive to negative, this is a maximum here. This is a minimum here. So we're going to have something like, let's see, negative slope to 0, right? Positive, and then negative to 0, and then positive. Something like this, right? Here we're going to have our 0. That's this one here. Here we have a maximum right there. And here we have another minimum right there, right? We got to do these in different colors. There's red. This is the red one right there. And this is the green one right here. Right? Because these spaces are where the derivative is 0. F prime equals 0 in this location right here. So you should be able to translate these graphs. F prime is 0 at that location, right? So that means that F prime is 0. F prime is 0 right there. Okay. So in general, what you need to think about is the following things. For F is the graph. For F prime, that's all the slopes of the tangents, right? And you need to remember that F prime equals 0 is a max or min. When F prime is equal to 0, that's a maximum or a minimum, right? When F prime, no, I'll do that. When F prime is 0, it's a max, right? And it's about increasing. I should say if F prime is positive, that means the graph is increasing. F prime is negative, that means the graph is decreasing. You also have a second derivative, right? This is the concavity. Concavity, right? If F double prime is 0, this is a point of inflection. Call that a point of inflection, right? Where the graph changes from concave up to concave down, right here. If F double prime is positive, that means it's concave up. And if F double prime is negative, it's concave down. So things to remember about graphs of slopes and equations, how to translate between these values, right? Another key thing to remember about inflection points, I just want to point this out to you. What do I do this in red maybe? I'll do this in red. Key thing about inflection points, these values here are where F prime is a max or a min. You have inflection points. The double derivative is 0, where the single derivative has a max or a min. So that would be like here is an inflection point. Because F double prime equals 0, right? And F prime is a max. So where your first derivative has its maximums, that's points of inflection. Right here is the inflection point. So that's at the same location that the first derivative had a max. And if we were to see the second derivative of this graph, if we imagine the second derivative, f double prime, at that location it's going to be 0 here and 0 here. Right here is also an inflection point right here. And so it's going to go, let's see, positive to negative to positive here, right? Positive, right? These are all positive slopes. So it's this positive area here. 0 here. There's my 0 inflection point right there. And then we have a bunch of negative slopes down to here, down to this inflection point. So this is all the negative points down here to this inflection point here where it's 0. And then we have a bunch more positive slopes, right? So f double prime is the slope, this is the slopes of the derivative graph. So just like, right, it's all a chain, it's all connected. The slopes of your original function tell you the derivative graph, the slopes of the derivative graph tell you the second derivative graph. So make sure you know about all of those. What do the last two for f prime mean? What do you mean the last? Oh, these mean the graph. I should write these words here. This graph is, that f is increasing and f is decreasing. This means the function itself, f, is going up, right? So if I'm positive here, like in this range here, between this minimum and this 0 here, that's this blue and this red. You see the graph is increasing in this section here. Because my f prime is positive, the graph is going up. My f is going up. And in this section between the red and the green, my f prime is negative. Between the red and the green, my graph is decreasing, right? Because it's negative here. And then after the green, it's positive. After the green, I'm increasing. So it tells you where I'm increasing, decreasing. All right. So make sure you know about graphs. Very important. I guarantee there will be lots of questions about this. Other things to remember about derivatives. Again, I'm recording this, so you should have this for you, is the particle velocity, particle motion, or just motion in general. When you have motion, generally x of t, or s of t, is the position of the particle. You know, maybe it's moving on the x-axis, is moving left and right, and so this tells you how far to the left or how far to the right you are. If you do the derivative of position, you get velocity. V of t is velocity. So the derivative of position is velocity. And velocity can tell you if velocity is positive. Positive means moving to the right. Negative means you're moving left. And if it's 0, that means you are stopped. Right, so if you imagine a velocity function, of the particle, right? Let me do this better. Hold on. Let's go like this. Right? The particle is stopped, if this is v, this is v of t, and this is t over here. The particle is stopped on these two locations here. It is stopped. It has ceased to move, right? It has ceased to move. In this area up here, the particle has a constant speed, constant positive speed, right? Constant positive velocity. It is slowing down in this section here. right? Slowing down. It has stopped. Down here, it is actually, in this green section, down here, it is actually speeding up. Let me move this over here. Stopped here, stopped. In this green section, my graph is actually speeding up. Speeding up backwards. Right? My graph is now going to the left, and it is going faster, right? I'm going to the right, I'm slowing down, I'm still going to the right, slowing down, now I've stopped, I've reversed direction, I'm speeding up backwards, and I reach a constant backwards speed. So here's a constant backward speed, constant negative speed, and then I slow down, and then I stop again here, and then I go faster, increase speed, and then I have a constant positive speed here, moving right. So we can break apart this this function here, this imagination of our velocity here, and we can imagine what the particle is doing at these locations. Increasing speed or decreasing speed, right? If it's going towards zero means you are slowing down. Towards zero means you are slowing down. Even if no matter if it's from the top or from the bottom. If you're going closer to zero, that means your speed is decreasing. Right? I'm slowing down here, and I'm slowing down over here. Slowing down to stop, slowing down to stop. If I'm going away from zero, I am speeding up. I'm increasing my speed. If I'm going away from zero, I'm gaining speed. And if I'm flat, I have no speed gain. I'm just a constant velocity. Okay? Now from that, we can do the derivative again and get acceleration. Right? It's the slopes of the velocity graph. Slopes of the velocity graph is acceleration. So when I'm flat, my acceleration is zero. Flat equals acceleration of zero. Flat means my acceleration is zero. So, for example, like here and here, I am not accelerating or decelerating. I am keeping a constant velocity, right? Flat means my velocity, right? If you think of the derivative of this spot here, that derivative is zero. This derivative here, along this entire section, my acceleration is negative. My acceleration is negative. So I have positive speed, my acceleration is negative, I'm slowing down, and then I stop, and then I have negative velocity because I still accelerate in negative direction, and I speed back up again. So with acceleration, it's kind of tricky. You have to think about what direction you're going. If velocity and acceleration have the same sign, you are speeding up. Speed up. Speed up. And if velocity, oh goodness, you slow down, you're slowing down. If velocity and acceleration have opposite signs. So if your velocity is positive, like up here, and your acceleration is negative, like as you have a negative slope, positive velocity, negative slope, you slow down. Here we have positive velocity and positive acceleration because our slope of this is positive. So we are increasing in speed here. Here decreasing speed, here increasing. The negative side, same idea. I have a negative velocity and negative acceleration. I'm speeding up. Here my velocity is constant, no change. Here my acceleration is positive and my velocity is negative. Opposite signs, so I'm slowing down, getting closer to zero. So your acceleration is the slope of your velocity graph. And you can use those to talk about position. All right, what else? We also have, okay, so we need to talk about the mean value theorem. Another piece of this is the mean value theorem. Mean value theorem. The mean value theorem relates to derivatives. And basically it says if f of x is differentiable on a to b, there is a c where f of c, f prime of c, I should say, equals f of b minus f of a over b minus a. So this is our mean value theorem. If f is differentiable, so first thing we have to be is differentiable. Must be differentiable. Must be differentiable. And to be differentiable, that means it has no sharp corners, no sharp spots, right? No corners, like, you know, anything like this. No corners here or corner here, right? No corners allowed. And it must be continuous. Meaning no holes, no breaks. Not even any corners that look like, you know, that have a, like a this, and then like sharp chain. Well, that's bad. Hold on, let me see if I can draw this better. Like it goes like this, and then like this. Like that's a problem here too. This is not allowed. Right? It's got a curve there, and then sharp corner, right? So any sharp corner is not allowed. To be differentiable means your derivative from the right side has to equal your derivative from the left side, right? F prime from the right has to equal f prime from the left. That's what differentiable means. And if you're differentiable, you're automatically continuous. If you're not continuous, then you can't be differentiable. So it has to be differentiable, I mean no sharp corners. If it's not differentiable, if there's a corner, it doesn't exist. And what you're doing is you find the average slope. This is the average slope right, from A to B. And so what you're doing is you imagine the graph, it looks something like this, right? From A to B, here's A, here's B. The average slope is the slope all the way across the whole thing from A to B. And f of c, this is a tangent slope. Tangent slope. And so there's going to be a spot somewhere where the tangent slope, and this is at C here, where the tangent slope is equal to the average slope. And so you have to find the derivative of the equation, find the average slope of the equation, and set them equal to each other. Okay? That's the mean value theorem. Again, you find the derivative of the function and the average slope, and you set the derivative equal to that average slope, and then you find this value c. Find the spot. All right, one more thing. I mean, there's a lot more. We didn't get into any about integrals. Let me go over here. Let me just add one more thing here about derivatives. There's also implicit differentiation. Implicit derivative. An implicit derivative is when you do ddx of an equation like 2xy minus 3x equals 5, right? And from this, you get a dy dx. I may not write it like that. That's kind of a bad idea. Right? You get a dy dx from the equation, and dy dx is the same as y prime. It's the derivative. And then you solve for dy dx. Remember, we rearranged that, right? This y is going to give you a dy dx. Solve for dy dx, you rearrange your equation, you get your dy dx by itself. So that was implicit derivatives, and there's everything about integration. All right. Got it, everyone? It's a lot of stuff. Key things. The intermediate value theorem is a key thing. Let me highlight these key ones. Intermediate value theorem is a key one. The mean value theorem is key. Mean value theorem is key. The graphs, being able to understand the graphs, that's key. And then definition of continuity. Those things are probably the main definitions they use, especially this graphing thing. Knowing what the mean value theorem is, graphs, and then there's stuff about integrals, which we have just done all those things about integrals, so hopefully you have all that. So I know we are out of time. I'm going to post this up to our Schoology page. Let me unlock that test for you all. Let me unlock the exam field. Where'd my page go? Oh, here. Publish that. Work on that. Take your time over the weekend. Send me any questions if you have any. And good luck. 30 multiple choice, 4 free response. It's due on Monday, everybody. We can meet on Friday if you'd like to go over some of those. But in the chat, say goodbye. Once you say goodbye, you're free to go. I'll see you next time.